Welcome to Chapter 5, and in this chapter, we're going to be sort of building up our skills to take a different look at individual trigonometric expressions and how we might add, subtract, multiply, divide, do factor, all kinds of different algebraic things to them to look at them in different ways and to look at ways that trigonometric expressions can be rewritten and how they might actually be equal to each other, but just in different forms. When it all comes down to it, all the trigonometric functions that we've looked at express a relationship between the x and y on a unit circle that is tied to a central angle. And that angle could be expressed in degrees, but more specifically and more helpful for us in trig is expressing them in relationship to the arc length, right? So the radians that that angle corresponds to. So we're going to look at building up our skills and sort of manipulating these things, looking for ways to simplify and re-express all the trigonometric expressions. We started off looking at it, and here we have just kind of a layout of how they are all interrelated with each other. And when it comes down to it, I'll go back to sine and cosine. Also, tangent being a little bit different in that tangent is expressing the relationship between sine and cosine in a fractional way, in a ratio way. And really what it's looking at is y over x, which has something to do with slope, if you recall our discussion of slope. So these are all kind of familiar to you. We also looked at some other ones, including the Pythagorean identities, which remembering x and y. Cosine and sine are really x and y. So when we talk about, plus they also mimic a triangle, right? They're the two legs of a triangle. And when we put that triangle into a unit circle, when we add up the squares of those sides, we have that radius of 1, that hypotenuse value of 1, which is always present in a unit circle. Also, we looked at the relationships between cotangent and cosecant. These are some identities that are laid out for us, some of which we will look at showing how they actually do interrelate with each other. Through algebraic means, we can prove those things. We've kind of been asked at this point to just kind of accept it. Maybe we explained a little bit more of the, sine squared, cosine squared. We haven't as much looked at these, but we also looked at the even odd. That if I have a sine function and I plug in a negative x, we actually end up getting the opposite of what we would have with a positive x. And so that is a odd function. But a cosine of a negative x actually produces the same thing we get when we have a positive x. And so that produces an even function. And the even functions only go with cosine and secant. All the others are odd. When we input the opposite of x, we end up getting the opposite of what we would get when we put in positive x. So what does it mean when we're verifying trig identities? All of what we looked at there, those one side is equal to the other side, is what we would call an identity. And those just are a sampling of some identities that we have. How can we verify them? Well, the way that we kind of do that is we lay them out, and we use algebraic operations to review the procedure for combining fractions by finding the least common denominator. So sometimes we want to add them together. So we're going to review how to use algebraic operations to do that. And review the fundamental trigonometric identities, looking for opportunities to apply the fundamental trig identities when working on either side of an identity. If we have a statement of equality, we say that's kind of an identity. So two statements kind of separated by an equal sign. We want to become thoroughly familiar with alternative ways of expressing these fundamental identities. And so how do we do that? What are some guidelines that we use? And so I'm going to be demonstrating these, but I want you to understand the approach that we're taking, right? If we have a statement that says one side is equal to the other side, we want to be able to verify that. And so some guidelines that we can use in doing that. Number one, start with the more complicated side. This is one that we use quite often. In many sides, one side you could say is a little more complex. Terms that are separated by pluses and minuses, squares, and so on and so forth. So what we generally want to try to do in mathematics is to make things as simple as possible. So sometimes we'll start with the more complicated side. It's easier to kind of put those together more, right? To try to construct them more to look like a less complicated side. And in doing so, if we can do that, we verified their equality. Also, stay focused on what it is we're after, right? As we're trying to decide what to do over on the more complicated side, we want to stay focused on what it is our goal is. What is the trigonometric function we're trying to consolidate it down to or to re-express it as? Another one option that we're actually going to use at the get-go here, but isn't necessarily always the best option. Sometimes it makes it even more complicated, but is to write one side of your identity in terms of sines and cosines. When it all comes down to it, all of these can be expressed in terms of sine and cosine. They're all just variations of that. Also, sometimes we might get to a point where we say, wait a minute, I don't know how to go forward on one side, or by doing so, I can see it's going to be much more of an uphill battle. And then sometimes we see, on the other side, I see something that I can use. So sometimes we'll kind of go on both sides and work until we have one side equal to the other side in our equality statement. So we're going to start out with the instructions here. We've got a trigonometric expression, right? It's not really set equal to anything, so it's not an equation or an identity. But the directions here say, let's re-express this in terms of sine and cosines and simplify what we eventually get. So this is one of those examples where we go back to, let's just look at it in terms of sine and cosine, because we know all of these can be written as such. So we kind of have done that here, right? We have cotangent x. Well, that's cosine over sine. Then we had tan of x, sine over cosine. And then we had a product of cosecant and secant. And cosecant, of course, is 1 over sine, and secant is 1 over cosine. So if we want to simplify this, simplifying a lot of times means let's combine things together. And the first thing, of course, that we can see here is that we have a statement of multiplication, right? These two can be written as one expression, 1 over sine x times cosine x. When working with fractions, multiplication and division are a lot easier to work with than addition or subtraction, right? So a lot of times we'll just start there. Now I've combined two of those into one statement, but I still have these other cosine x, sine x being added to sine x, cosine x, and then being added to that third expression. Well, what would be helpful for me here is to actually be able to add all three of these together and put them into one expression, right? So when we approach that, we want to look for what would be the least common denominator, the LCM, if you will. least common denominator being LCD, least common multiple, LCM. We're just talking about the individual factors themselves. We're talking about what is the multiple, what is the thing that they could all multiply into, which when we put it in the context of fractions means what is a denominator that we could get all of these expressions to have, right? And generally you want to look at what could be multiplied into these expressions. When we take a fraction, and let's just take a simple fraction like 2/3, the only way that we can really rewrite this is through multiplication. Because when we multiply the top and the bottom by the same number, we're in essence multiplying it by 1. So we are retaining its value we're retaining its value but changing the way it's expressed, its expression. And so looking at the three denominators here, we have sine x, we have cosine x, and then we have the product of sine x and cosine x. So if I wanted to rewrite and get a common denominator that I hence could add all these parts together, the one I'm going to want is this more complicated one, right? The sine x cosine x. Because the only option I have is to multiply each individual term by something in order to, you could also divide, but that wouldn't solve the problem here. We want to get the same thing in each one of these things. So we're going to multiply the top and the bottom of each, and so that it looks like this product. A least common multiple will always be the product of the smaller parts of the other denominators, right? The smaller parts of our other factors. If we were adding, for example, this kind of mirrors what we have here. Let's say we had to add these three together. 6 here, if we look at what it's made up of, is made up of a product of the other two. And so we say 6 would be the least common denominator we could get here because it's made up of multiplying the other two denominators. And so I can multiply the top and the bottom here by 2, and I can multiply the top and the bottom here by 3. And that will give me that common denominator 3/6 plus 2/6 plus 1/6. And so that would give me 6/6 or 1. So at any rate, that's kind of that process. Now let's think of sine x and cosine x as kind of like your 2 and your 3. They both go into the product of cosine x and sine x. And so that's what we're going to use to simplify this. So I've decided on my sine x, product of sine x and cosine x is going to be the easiest way. Let's do what we have to. So for my first, I see I'm missing a cosine x. So I'm going to multiply the top and the bottom by cosine x. And here I'm going to multiply the top and the bottom by sine x. And for the third expression, I don't really need to do anything. I already have that. So cosine x times cosine x is cosine squared x. Notice how we write that. We put the squared next to the cosine because it's the result of taking the cosine of x that we want to square. We don't want to square. For example, we wouldn't want to write it like this without parentheses. With the parentheses, we're okay. But generally, without it, that square would only apply to the x. It would not apply to the cosine, right? So taking the cosine of an x that we've squared is different than taking the cosine of an x and then squaring that result. So cosine squared x generally is how we'll write that, over cosine x sine x. And then we have sine squared x over cosine x sine x. And then we're adding 1 with, again, you could write a sine x over sine x cosine x or cosine x, putting an order to the multiplication. It doesn't matter. You can write it either way. Oops, and I forgot the sine squared there. All right, now this can be written as one statement. Cosine squared x plus sine squared x plus 1 all over the same denominator, cosine x sine x. And you could have it as, again, sine x cosine x. It's in multiplication, 2 times 3 is the same as 3 times 2. It doesn't matter what order they're in. Now that I have this here, I want to look for ways that I can continue to simplify this or to rewrite it, because it doesn't look like we've necessarily simplified this very much. And here we do notice something. Remember that the Pythagorean theorem said that cosine squared x plus the sine squared of x results in a 1. And so that expression right here, I can just rewrite as 1. And that gives me a 1 plus 1 on the top over cosine x sine x. And of course, it makes sense to just add those ones together. And that gives me 2 over cosine x and sine x. At this point, I don't see any other way for us to really simplify this or to rewrite it. We've definitely simplified it in the sense that we've added all the parts together. And we have a much more simplified expression than what I have above. Even if it was equally maybe complicated, we've at least rewritten it into different terms. But I think you would agree that we've simplified quite a bit there in combining all these together. Another approach we can take on some problems, or that we're asked to take on a problem, is to prove that something is not an identity. It's a little bit harder to do that. You would have to get to a point where both sides completely disagree with each other logically, and that you could look at and see there's no way, except for maybe a couple of exceptions. The tricky part is some values of x might prove these to be true. Or, if we were to plug in a particular x, sometimes we end up getting, we maybe accidentally or whatever, pick something where the left side does come out equal to the right-hand side. But if we can pick something as a value for x where it doesn't, then we've proved it's not an identity. Because if it is an identity, it has to be true, and it always has to be true, right? So let's take a couple approaches to this. One of the approach is to do what, like we did on the previous one, is to manipulate the statements themselves, to carry out some of the operations that are present. When I look at this, the left-hand side kind of stands out a little bit more. This is something I can actually do something with. There'll be stuff I can do with on the other side as well. But let's start with the left-hand side. What happens if I actually square sine x minus cosine x? This is actually, this statement is something that people will accidentally do sometimes, thinking that they're carrying out the correct operations. In other words, people will take a addition or a sum, and they see the square, and they distribute that square to both parts. And in actuality, this doesn't work. It doesn't carry out. This is almost exactly the type of, except it would be y minus x with sine. But this is something you're a little more familiar with through algebra, right? That when we have a addition or subtraction squared, we actually want to write it as sine x minus cosine x times itself, sine x minus cosine x, and use FOIL to actually carry this out correctly. And so doing that, we'd have sine x times sine x, which is sine squared x. We have sine x times negative cosine x, so minus sine x cosine x. And then we have negative cosine times positive sine, so another negative sine x cosine x. And then we have a negative cosine times a negative cosine, which gives us positive cosine squared x. And combining like terms, or what have you. These two obviously can be written together. There's two of them. They're the same products. So we can rewrite them as minus 2 sine x cosine x. You could also have that as cosine x sine x, either way. And we can also see that, I have a positive cosine x, a positive sine x, and we know that adding those two together give us 1. And so that would give us 1 here, and then minus 2 cosine x, or minus 2 sine x cosine x. So far, I haven't gotten something that mirrors what I have over here. But maybe there's stuff I'm missing. So now I might turn to this side and say, are there ways for me to simplify what I have over here? I know that sine x plus cosine x, cosine squared x, add up to give me 1. And this gives me a way to rewrite sine. If I subtract cosine squared x to both sides, I can see sine squared x is equal to 1 minus cosine squared x by subtracting cosine squared x on both sides. So that's something I could do. I could rewrite sine squared x as 1 minus cosine squared x. And then I have this minus cosine squared x, right? This is what I still have here. And I did that only to get it so that it looks like the other one, right? So we have 2 cosine squared x, which can be rewritten together, 1 minus 2 cosine squared x's. Which, cosine squared x means cosine times cosine. Notice what I have here is not cosine times cosine, but sine and cosine. And there are times where cosine x and sine x have the same outcomes. There are certain times that they do, but most of the time they do not, right? Sine is y and cosine represents x. So for any given angle. So because of that, I can definitely say these are not equal to each other. We can also just, though there may be times where they are, there are some radian values where we would see them equal to each other. Pi over 4, 45 degrees, I believe would be one of them. But that doesn't make them an identity, right? But in terms of identity, if we are making this statement of equality, it's like saying somebody is innocent, right? Or not guilty or something like that. We only need to come up with one example to kind of disprove that. And so another method we could use is let's plug a value in for x. Let's see if 0 works. 0 is always nice because at 0 degrees, when we talk about it, is going to have a very concrete value for sine and cosine. So if we substitute x equal to 0 here, we can see, hey, do we get two statements that are equal on each side? Maybe we will, maybe we won't. I actually don't know. I don't think we will, but let's see. So that would give me sine of 0 minus cosine of 0 squared. And on the right-hand side, I would have sine squared of 0 minus cosine squared of 0. We'll see. Sine of 0 is the y at 0 degrees, which is 0. And cosine of 0 is 1. So this gives me negative 1 squared, which is positive 1. Is that equal over here? Well, sine squared 0 again is sine of 0 is 0, and 0 squared is 0. And cosine of 0 is 1, and 1 squared is 1. That gives me 0 minus 1, which is not positive 1, but negative 1. Because these two sides are not equal with the one example that I picked, that already disproves this as an identity. Be careful, though, as you're doing this and you don't think in terms of what you're really wanting and trying to make it fit, even if it doesn't. That's always a temptation. For example, here you might say, well, we're squaring minus 1, but we're not doing that. We're squaring 1 and not the minus here that's in front of it. That's a subtraction. Yes, we sometimes conflate those two, and sometimes we state them in terms of minus 1, but really it's a subtraction of 1. And if we subtract 1 squared, that's minus 1. Even though minus 1 itself, if we include the negative, is positive 1, we're not including it. The squared only applies to the result of cosine of 0. So let's take a step forward here and look at how we can verify trigonometric identities. We've kind of gone through some of those steps, but the basic idea is to verify an equation as an identity. We want to transform one side of the equation into the other side by a sequence of steps, each of which produces an identity. The steps involved can be algebraic manipulations or can use known identities. Note that in verifying an identity, we do not just perform the same operation on both sides of the equation. We're really usually just working on one side, trying to make it look like the other side. What's kind of nice about these identities is that we get to be a little creative with trying to look for those types of relationships using the different identities that we know to be true. And also we kind of see a goal on the other side, right? Here we see we want to get this down to be just a simple cotangent. That's a very lofty goal in a sense. And so we're really just focused on not treating this like an equation necessarily, but manipulating and changing one side. So that doesn't always necessarily mean multiply both sides by blah, blah, blah. We're looking at this more like, let's manipulate this expression until it looks like what we have on the other side. This side is the more complicated side. That was one of our strategies that we had. And so the first thing that we may do here is notice that there is a relationship, a Pythagorean relationship between cosecant that we have. Looking back at our Pythagorean identities, we can kind of see that. We do have an expression involving cosecant here where cosecant squared x is equal to 1 plus cotangent squared x. And of course, these can be rewritten in lots of ways, right? I can set it equal to cotangent by subtracting 1 on both sides. So cosecant squared x minus 1 we know is also equal to cotangent squared x. And we could write it in terms of, cosecant and cosine. Cosecant, this is cotangent, not cosine, is equal to cotangent squared x. And we can put these on either side, where cotangent squared x minus cosecant squared x is equal to negative 1, and many different things like that. So let's go back to our slide and see if we can apply any of those. Back here, we can actually see that cosecant squared x minus 1 was equal to cotangent squared x. When we subtracted the 1 to the other side, that's what we got. So I know cosecant squared x minus 1 can be rewritten as cotangent squared x, period, divided by cotangent x, which we have in the denominator. And there we have two common factors on opposite parts of a fraction, which can be multiplied into, right? We have two cotangents x's on top and one cotangent x on bottom. So one of these can cancel one of those two, which takes us down to cotangent x. So now my left-hand side is equal to the right-hand side, and we have verified this statement of identity. Let's take a look at another one. Again, we kind of want to start with the more complicated side and see what we can do there. So, of course, I'm going to veer to the left-hand side because it's definitely a little more complicated. If anything, it has more stuff in it, right? And we want to just start with something here. if we want to go back to the initial relationships that we see with everything being related to sine and cosine, I could say, well, this is equal to 1 over cosine theta minus cosine theta. And then, of course, we want to put that sine theta down here. Can I write them together? Can I combine these? And I can, because this is cosine theta over 1, if we get a common denominator there. So let's multiply the top and the bottom by cosine theta. In doing so, let's write what we have left after doing that. That gives me 1 over cosine theta minus cosine squared theta over cosine theta. And then, of course, everything over sine theta. Remember that as you go, you want each rewrite to be equal to the previous. Otherwise, you'll start losing stuff if you just focus on the top and forget about what's on the bottom. Every time you do this, we're saying equals, right? And so that statement of equality needs to hold true as you go forward. Always rewrite the whole expression, even if it's extra work there. I should be able to follow what you're doing. And if you leave parts of it out, you're going to forget about parts because some of these get more complicated as we go. But now we have something there. We can combine those together. That gives me 1 minus cosine squared theta over cosine theta. The top part there is written as a single fraction now. And what I have on the bottom is sine theta. So remember, I wrote these two fractions as one fraction. The fractions within fractions can start to look complicated. So you want to keep this going. Remember to think about, look back, have I forgotten anything about what I had there? And we know that cosine squared theta plus sine squared theta equals 1. And if we subtract either or to the other side and subtract it from 1, we're equal to the other squared. So again, I'm going to rewrite this. 1 minus cosine squared theta is actually equal to sine squared theta according to the Pythagorean identity. Cosine squared theta plus sine squared theta equals 1. So you can subtract, this to the other side, and it's equal to the other. And you can do that with either of them. So that's now sine squared theta over cosine theta divided by sine theta. And if I were to write this out, remember a fraction is a sort of division. I mean, it is a division. It's a form of division. So this is, we can take this sign out here and say, let's rewrite this. And instead of, I'm going to rewrite this as a separate expression, sine squared theta over cosine theta divided by sine theta. Usually when we divide these fractions, we multiply them by their reciprocals. So that would be the same as sine squared theta over cosine theta times, this is sine squared over 1, or sine over 1, times the reciprocal of that, 1 over sine theta, which is going to cancel out one of my sines here. And that just leaves me with sine theta over cosine theta. You see, you want to give yourself a lot of room here as you're writing these out. Now, as you substitute and do these on the computer, you don't have that work to show, right? But that kind of work you will need to show on the next test. A lot of times they're saying verify, but really that verification is this step-by-step rewriting. So give yourself a lot of room on paper. Don't try to cram it into tiny little spaces on your paper. You and I should both be able to look at your work, and I should be able to see the process that you went through. And that takes practice, and I'm going to try to demonstrate that as much as I can. But again, our ultimate goal here was to make the left-hand side equal to the right-hand side. We've done that. So we've verified this identity. we're going to take another look at another example where we can rewrite them using sines and cosines. Again, that's a very common way that we can even just start to simplify these and to transform one side into the other side. So in this one, when we start looking at it, we see the sum of two statements, cotangent to the fourth plus cotangent to the second. And here we have a cotangent of x times the cosecant squared of x. So we say, well, which side is more complicated? Generally, the left side in this case doesn't matter left or right, but because this is a statement of addition, we say this is a little bit more complicated, and think about it in terms of what we have to do. If we want to try to combine these together into a single statement, we're going to have to get a common denominator, right? Which is a much much more complicated task than a statement of multiplication. And so that's why we say the left-hand side is a little bit more complicated. So we're going to start trying to transform this into this, right? So I can draw my line a little like this. Here's where the other side is. Cotangent squared x, cosecant squared x. All right, so what I've done is started out rewriting these involving sine and cosine and their squares. So rewriting the two cotangents and then looking at the denominators and saying, how can we make one look like the other? And the obvious answer comes by adding a couple more another sine squared x here will give us sine to the fourth power x. So we'll multiply both sides by the sine squared of x, not both sides, sorry, the top and the bottom of that fraction by sine squared x. And that'll give me common denominators. So cosine to the fourth x over sine to the fourth x. Again, rewriting it, taking those extra steps. And then I have cosine squared x times sine squared x over here, divided by sine to the fourth power of x. Now we have common denominators. We can write this as a single statement, cosine to the fourth x plus cosine squared x sine x squared x. Don't forget the x's in there. And the squareds all over one denominator, sine to the fourth x. Still doesn't look like what I have over there, right? Not quite there yet. However, I can notice that across this plus sign, there is a common factor there that I could choose to factor out. That will at least change what I have on the top into a statement of multiplication rather than a statement of addition, right? So when we factor, we're undistributing it. It's like what I like to say. There's two cosine squareds on either side of the plus sign. So I'm going to factor out cosine squared x. And then we put what's left. Well, I still have two cosine squared x's here, or two cosine x squared. I'm saying that incorrectly. Two cosine x squares. No, that's correct. And on the other side, now I only have sine squared x. Right? I took out the cosine here and here. So I'm left with two cosine squared x from here, and I'm just left with the sine squared x for here with that plus in between. Redistribute that, and you can see that's what, we did that correctly. That's one way I always double check my factoring is by redistributing it, at least in my mind, and saying, would I have that? Well, yeah, I would have cosine to the fourth x, and then I would have cosine squared x times sine squared x, which is what I have there. So I've done that correctly. And I see a relationship here, my Pythagorean identity there with the cosine squared x, sine squared x. So this can become 1, which then leaves me with just cosine squared x times 1, which is cosine squared x over sine to the 4th of x. Again, still don't have what's over here, but I have it written as one statement there. Here's where we might take the decision or make the decision to say, well, this is written as one fraction here. Could I rewrite this in a way where it would be one fraction? And take the initiative and go, well, what is cotangent squared x? It's really cosine squared x over sine squared x. So here we're deciding, hey, let's rewrite the other side and see what we come up with. And cosecant squared x is 1 over sine squared x. Again, it's easier to put things together than to try to pull them apart. Like I could try to pull this apart to look like what we have over there, and we could do that, but we actually, if we do the multiplication here, can see really quickly that cosine squared x times 1 is cosine squared x, and sine to the squared x times sine squared x is sine to the 4th power of x, which is exactly what I have over here. So we used one of those other strategies where we get to a certain point and we say, well, let's start working on the other side. It's easier to put things together, to carry out multiplications, to carry out additions and subtractions than it is to kind of undo those, which is like what you experience when you try to factor, right? When we factor, we have to try to undo things. We have to undo a distribution of cosine x, and that's trickier for our minds to see. So there are points where we might want to try to eventually just get the right-hand side equal to what we've simplified down to on the left-hand side. The goal is make one side equal to the other side. There isn't always just one way of doing it either. And in fact, sometimes if we try to always just put it in terms of sine and cosine, we'll find much more complicated ways of doing it. Another approach that we could have taken is to say, look, these are both the same thing, right? Written across a plus sign. They're both cotangents, and they both have at least 2 cotangents, right? There's 2 of them here, 4 of them here. Cotangent x times itself 4 times, cotangent x times itself 2 times over here. So let's actually do a factorization of cotangent x. If I factor out cotangent squared x, they all have at least 2 cotangents, right? That leaves me with 2 cotangents here and 1 over here. Cotangent squared x divided by itself is 1. And at this point, I think we have another identity here that we can look back at our previous list there. And here we see that 1 plus cotangent squared x is equal to cosecant x. So applying that idea, my cotangent squared x plus 1 is simply equal to cosecant squared x. And now we've done this in basically 2 steps rather than the other one. So when I rewrite expressions using only sines and cosines, it isn't always the quickest way to verify an identity, but it can help us if we can't see any other relationships there, right? And for these identities, you're not going to see the endpoint right away. All you can really see, and this is the key to learning this thought process, is to try stuff. You really just have to try stuff. Look for relationships. think of the different operations that we have. We always think of plus and minus as being kind of the lowest level of operations, and the most difficult as well. In certain instances, adding and subtracting fractions is really difficult when we don't have that common denominator. There isn't always just one way, but what you want to be able to show on a test is that each time you're rewriting this, you are writing something that is equal to the previous statement, one step at a time. So if there are fractions involved, keep those fractions there. Don't just try to simplify the top and then slip the bottom denominator in once you've done all that stuff. Each time you rewrite it and use an equal sign, you're saying this statement that I'm about to write is equal to the previous statement, and you never want to violate that. And that's what I've done here. Each time I rewrote it, I included everything, and that's one of the most important things to follow. The second thing is it sounds very simple, but just try stuff. Here we go again. We have a statement which is said, this is an identity, right? These two are identical to each other. They are equal to each other. And so what we want to try to do is rewrite this until it looks like the other side. What side do we start with? Well, this side is written as one fraction. This side is written as a subtraction of two fractions. This is the more complicated side on the left. So that's what we want to do. It's easier to put things together than to take things apart. And that's especially true when we're talking about identities. So 1 minus sine x is one of the denominators we have here, and 1 plus sine x is what we have there. Those are not equal to each other. In fact, they're opposites. However, we can get common denominators by multiplying them. In other words, my least common denominator here, or LCM or LCD, however you want to think about it, would be the product of 1 minus sine x times 1 plus sine x. I know that sounds like something you don't want to do because it looks really complicated, right? But these are two things that have absolutely nothing in common. It's like having two denominators where one is a 2 and one is a 3. Sometimes we're just left with two things that we have to multiply in order to get a common denominator, 6. So I'm going to multiply this side by the thing that it's missing, which is the plus sine x. And I'm going to multiply this one by 1 minus sine x. And we'll do it on top and bottom. So again, this is one of those things where you want to take that extra step to write those in. I should be able to see that and say, yep, they didn't violate anything just by multiplying the bottom. And you don't want to deceive yourself. You want to see clearly to your next rewrite, right? So this is 1 plus sine of x times 1. Remember that there's a 1 here, but if this was a 2 or something, you would want to distribute that 2 to both of these. So that's why I put it in parentheses, just so I remember that. That's true when you have things separated by pluses and minuses. Put a parenthesis around that so that if there's a number here, you would remember to distribute it if there was something there other than a 1. But times 1 is still equal to just itself, so we have 1 plus sine x times 1 plus sine x times 1 minus sine x. What do we get if we multiply this? This is a product of a sum and a difference. And we know that gives us, if we FOIL it out, gives us the difference of 2 squares. In other words, 1 times 1 is 1, so that's 1 squared. Which 1 squared I know is 1. I'm just doing that right now for a purpose. Positive 1 times positive sine x is positive sine x. Negative sine x times 1 is minus sine x. And then minus sine x times minus sine x is minus sine squared x. And see, with the product of the sum and the difference, the 2 in the middle always cancel out. And so we're left with the difference of 2 squares. We're left with the subtraction of the 2 parts squared. 1 squared is 1, so I'm just going to write this as 1 minus sine squared x. We know that's the product, the eventual product of both of these denominators. And then we're subtracting. Again, we just have a 1 times multiplication of 1, so we just get 1 minus sine x there. And then we end up with that 1 squared minus sine x squared, or 1 minus sine x squared. So now we do have common denominators. Let's rewrite it as a single denominator. Remember that these are 2 terms, 2 things separated by a plus or minus. So this subtraction we need to distribute this negative to both. So we don't forget to do that. So that gives me 1 plus negative 1, which is 0. And then I have sine x plus sine x, so sine 2 sine of x's. Oops, where's the n? There we go. Sine x plus sine x is not sine squared x, right? Sine x plus sine x is 2 sine x. Sine squared x we would get if we had sine x times sine x. But we just change the coefficient out front when we're adding them. So I have 2 sine x over 1 minus sine squared x. I'm still not looking like what I have over on the right-hand side. Maybe we should try to rewrite this again. I notice this 1 minus sine squared x. Again, that is a Pythagorean identity. 1 minus either cosine x or sine x gives us the other. So that actually gives me, so here I would have 2 sine x on top over cosine squared x on the bottom. I don't know where to go from here. Like, I've kind of come to the end of what I could simplify over here. Sine x doesn't simplify with cosine x. So we're kind of stuck at that point. Now I'm going to maybe turn to the right-hand side again. This isn't necessarily simple, but it is. It was simpler than the original statement. So are there ways for me to simplify what I see over here? And here I've got a lot of squareds on top. I'm thinking one of these can be rewritten in terms of another statement. Let's go back to the original. So we have a tan squared x plus a cosecant squared x and a plus 1. So that plus 1 may come in handy to us, or just rewriting secant squared as something else, or tangent squared as something else. Let's go back to look at our list. Looking through here, we do see actually a direct relationship between tan squared and secant squared. Those are the 2 things that we have there. So I'm going to just go ahead and rewrite the tan squared x, though we could also rewrite the secant squared x. But I'm going to rewrite the tangent squared x as secant squared x minus 1. You have a choice there. We can also rewrite the secant squared x that we have. Either way, like I said, a lot of times there's different ways of going about this. So I'm going to take my tan squared x and rewrite it as 1 minus secant squared x minus 1 is how that we subtracted that 1 to the other side. So this would be 1 minus secant squared x, or secant squared x minus 1. So secant squared x minus 1, I'm substituting this for the tangent squared. And we have plus secant squared x, and we have that plus 1 still here. And I can see that plus 1 and minus 1 is going to go away. And so that would leave me, this is over cosecant x. Let me demonstrate rewriting. And so that top part, I can rewrite. The ones cancel each other out. And I have secant squared x plus secant squared x. So 2 secant squared x's. Secant plus secant. Well, secant plus secant. And, x plus x is 2x. X squared plus x squared is 2x squared. That's similar to what we have here with the square. And here we have cosecant x, cosecant x. Still not the same, but we know there's a relationship between secant and cosecant. Let's rewrite these in terms of their sines and cosines. On top, I have 2, and secant is 1 over cosine squared. And on the bottom, I have cosecant, which is sine, 1 over sine x. So 2 times 1 over cosine squared x times the reciprocal of 1 over sine x would be sine x over 1. So I'm doing that division by 1 over sine x, which flips the bottom. And that gives me 2 sine x. This is still 2 over 1, so it's going to go with the top. So 2 times 1 times sine x, so 2 sine x over cosine squared x, which is what I had on the left-hand side. You can see that we went far enough, well, as far as we can kind of seemingly go. Keep pushing it, but at some point we may want to turn to, let's take another look at what we have on the right, because it's pretty complicated too, right? These were all pretty complicated. The thing that separated the left a little from the right is that it involved a subtraction of 2 fractions where all of this was in a single fraction. And so at least initially, the left-hand side was a little more complicated. But by the time we manipulated them on both sides, we were able to come up with the same thing on both sides. So we've proved that identity. You recall on the last one that we had, we had something similar to this 1 plus sine x here. And we saw that difference of 2 squares when we multiplied it by 1 minus sine x. That is called a conjugate. The conjugate of 1 plus sine of x is 1 minus sine of x. When we multiply those, we get the difference of 2 perfect squares, the subtraction of the 2 parts squared, using FOIL and all that. And so that is a commonly used thing when we're trying to transform, is sometimes to use that really powerful formula which eliminates the middle term via FOIL to solve. So that's another thing to look for is I have 1 plus sine x. Let's try multiplying it by 1 minus sine x on both the top and the bottom. And sometimes this gives us something helpful. Again, we got to try stuff. So what happens when we multiply it by its conjugate is we get the 2 perfect squares. In other words, actually, let's just do, in general, this is how we're used to seeing it. X plus y times x minus y gives us x squared minus y squared. The 2, when we use FOIL, we get the x squared. Then we go x times y, and that's a negative y, so it's minus xy. Then we go the inners, xy, and those are both positive, so plus xy. And then we go the last, positive y times negative y is negative, positive times negative is negative, y squared, and the 2 cancel out in the middle. So we can kind of skip that whole process, and knowing that rule there of conjugates, this is going to be 1 squared minus sine squared. 1 squared, of course, is always just equal to 1. So I can just write 1 minus sine squared, and then we have cosine x on the top. We don't have just cosine x on the top. We have cosine x times 1 minus sine x, so I want to do that distribution. That would give me cosine x minus sine x cosine x. However you want it, whatever order you want to put those in. All right, that's still not the same as what we have on the left, but I do have a 1 minus sine squared x here. And on the top, let's see. Oh, and this can be simplified down to a cosine, which has taken us a little bit closer to what we have. This would be cosine squared x, of course, by the Pythagorean theorem. And on the top, I can see something here. On the top, if I hadn't distributed, so I'm going to undistribute here. So if I just left it as cosine x times 1 minus sine x, there's something that can cancel because we have cosine of x on both sides, and now on the bottom we have cosine squared x. Rewriting it as a product, that's when we can cancel. Remember, we cannot cancel across plus or minuses, but in doing so, I get 1 minus sine x over cosine x, which is what we have on the right. I always have to kind of look at what's on the right and say, but at each stage here, notice I rewrote it. What do I have? What do I have? Rewrite it, rewrite it. This is the thought process and the writing process you want to go through. Writing equals thinking. You can't think about it if it's not written. It's kind of the rule that I use. So I like to write out everything. Of course, there's another approach we could have taken to this whole thing. This is a one fraction equal to the other fraction. And if I do a cross multiplication, we might be able to see where they actually do come out equal to each other. This is a bit of a violation of the process of using an identity because we're treating it like an equation. But if I do that, that gives me, cosine x times cosine x, which is cosine squared x. And then we have the product of a sum and a difference here, which is going to be a difference of two squares. So 1 squared minus sine squared. And 1 squared, of course, is equal to 1. So I'm just going to leave that out. And then we can easily show here on the right that this is equal to cosine squared x. So in doing so, we have shown, hey, this equality is a true statement. When we use cross multiplication, if I have a over b said to be equal to c over d, if I look at their cross products, in other words, a times d, it should equal the same product I get with b times c. And that's another way we could have shown that these two things are identical. So just to review some of the strategies we used here. Algebraic operations, we review the procedures for combining fractions by finding the least common denominator. So we're going to use algebraic operations to kind of rewrite things. We're going to use the fundamental trig identities. Sometimes this will actually save us a lot of time. It's not always easy or the best way to always switch them to sine and cosine and to rewrite them, but that is helpful as well. Start with the more complicated side as you're doing this. So look for fractions that need to be combined together. That's a complex operation, and it's going to make it easier when you can practice simplifying the more complex side. It's easier to put things together than to take them apart, at least when it comes to identities. And stay focused on the final expression, looking at the other side. You're not going to see 3 steps ahead, but as you continue to look back at the final expression, as you start to simplify one side, you'll start to see connections there as you go. We can convert it to sine and cosine. Kind of want to make this the last thing, but because it tends to give us more steps. But there are times where that's just helpful. And then to work on both sides. We can get to a point where we get stuck on one side and we don't know what to do, and so we start working on the other side. Conjugates is another thing to look at. When we multiply these two together, we get 1 squared minus sine squared. And look what that always produces. That's just 1 minus sine squared theta, or x, which can be condensed to cosine squared x. Same is true for 1 plus cosine x times 1 minus cosine x. Secant times tangent. Secant and tangent, if we think of secant and tangent, secant plus tangent, when we multiply it by its conjugate, we get secant squared x minus tangent squared x. And both secant can be written in terms of tangent. Tangent can be rewritten in terms of secant. That offers us ways to combine them together into one expression rather than two. So it's that with the Pythagorean identities, etc., will help us rewrite, simplify, and try to make the left-hand side look like the right-hand side, or vice versa. Have fun with these. That's kind of the important part. It is a little bit frustrating to start out when you're doing this because it requires a certain type of thinking. But I encourage you to, like I said, one of the best pieces of advice with working with this is not to just sit and stare, because you won't see it necessarily at the outset. You just have to try some stuff, rewriting it. This is going to be a real challenge to remember some of those algebraic skills, and that's really what you have to work through. But try stuff that you know is equal and try to really carry that out using the rules that we've used in algebra. Good luck as you start going through and verifying trig identities.